everyone, good evening and welcome to India's first animated live tuition. Hello everyone, good evening, good evening. Yes, are you all ready for the class? Packed with energy, right? Am I right? Are you all packed with the 100% energy? Yes, right? Let me check that. So, first of all, turn on the camera. Quickly turn on the camera. I can see so many cameras there. So, please do turn on the camera and we'll do something, okay? So, quickly turn on the camera. I'm here, so I want to see everyone. So, quickly turn it on. I'll give you 3 seconds, okay? And the countdown starts now. 3, 2, and 1. Here we go. Yes, very good, very good. So let me check the energy that you have. So everyone quickly stand up from your positions. Quickly stand up. Everyone. I want everyone to stand up from your positions. Quickly do that. Let me check your energy. Yes. So everyone is standing up, right? No, they're not? Why? Quickly stand up. Everyone. Yes. Who's the one who's not standing up there? Yes, call out their names, sir. Yes. Quickly stand up or else I'm going to call out your names, okay? Quickly stand up from your positions. Let me check your energy. Yes. And I hope everyone standing up. Yes, very good. Quickly turn around. And stretch your hands. Quickly stretch your hands. And do a sit up. Sit up. Or if you want to do the push-ups, you can, okay? Take 2 push-ups and come back. Or sit up is just enough, okay? Yes. Very good. So, someone is really exercising over there. Very good. So, you're all packed with energy, right? So, no one is in sleepy mood, right? No. Because we are going to study some important topics today. So, no one is going to sleep during the class, okay? So, if you're feeling like a sleepy, just get up from your position, stretch your hand and do a sit-up and listen to the class again, okay? And you know that it's a YouTube live going over there, right? You know that, right? And we have a link provided in the comment box. What do you have to do now? Yes, you're going to quickly share it with your friends and you're going to put that in your status, okay? Yes, will you do that? Give me a thumbs up if you'll do that. Quickly share the link with your friends and let them know that we are conducting a YouTube live over there and we are going to discuss some important topics. Let's study together, right? Yes, helping mentality is always good for us. So, yes. And do we have any new students in our class? Do we have any new students? You can just raise your hand. Raise your hand if you are a new student. If you are watching me for the first time or is this your first class, you can just raise your hand. Yes, unmute her, ma'am. Sir.
Smia.
Nia.
Smia.
Smia. Hello, Smia. How are you, Smia? Going good, and I'm also doing great. So, where are you from, Smia? Kerala. So, which part of Kerala? Thrissur. Very good. So, have you seen the Thrissur Puram? Not really. Very good. So, in your school, do this chapter started? Matter in our surroundings? It's already started, right? And we are almost at the end of this chapter, okay? We are almost at the end. We are not going to wind up the chapter today, but we are almost at the end, okay? I hope you can follow everything. Yes, and welcome to our class, welcome to chemistry class and to our family 90 plus. Yes, and do we have any other new students there? Yes, over there, the first one. Yes. He's not a new student, but he's raising his hand. Who's that? Mars. Yes, Mars. I couldn't see your name over there. Yeah, Mars.
So is there like a new chapter we started?
What was that?
Any new chapter?
You want to start the new chapter? Leaving this chapter behind?
No, because like I'm already like a pro in this chapter.
You're pro in this chapter, so
Yes.
but other students are not. Not like
teach
you,
them.
right? So everyone is not pro like you. I have to teach everyone, right? Yeah, not only the student in this class. We have so many of them are here, so we have to teach them all. So must just wait for it, okay? We'll wind up this chapter within 2 days, within 2 classes, okay?
2 days.
2 classes, within 2 classes.
2 weeks, mate. 2 weeks.
2 weeks, yeah, maybe, according to the timetable.
Because there's only one class per week.
Yeah, next week timetable is not at here, so we'll decide then, right? Okay. So, do we have any other new students? No, right? And do you have anything to tell me? Yes, unmute them, student.
Devyani.
Devyani.
Hi.
Hello. Where are you from, Devyani?
Karnataka, Mangalore.
Mangalore. Very good, very good. So, is this your first class or is this your first chemistry class?
First chemistry class.
First chemistry class. So, you have been there in physics or maths class, right?
Yeah.
All right. And I have told you the chapter that we are discussing is nothing but matter in our surrounding, and we are almost at the end of the chapter, okay? Hope you can follow it. Welcome to our class. All right. So, rest of you students, I will introduce you or we'll get to know each other day by day, okay? We'll get to know each other day by day, so no worries. Now, let's begin the chapter. I think my exams are on 14th course on my friend told me, but I'm not sure. So, we'll check it out, okay? 14th. Alright. Ma'am, I'm new. Alright, welcome. All the new students, welcome to our class, welcome to our session, and welcome to our family 90 plus. Alright, so we are going to begin the chapter with an animation. Yes, okay, so the animation. We'll begin this chapter or the portion with an animation, okay? We have already played this animation in the previous session too, but we are going to learn this now again, okay? Let's recollect the points again, okay? Yes, so you can play. What is this? Yes, what are the things that we discussed in the previous session? What was this? What were we discussing? What were we couldn't complete the portion, right? So what were we discussing? You can comment it. Be interactive. Please do be interactive in the class. Comment it, okay? I want the answer from everyone. Be interactive. Everyone must be interactive in my class, especially in my class, okay? So be interactive. Yes. What was the thing that we were discussing in the previous session, but we couldn't complete it? Then I told I'll discuss that in the next session, and here I am with that again. Yes, very good. Latent heat. You remember what is latent heat, right? It was nothing but latent heat. So we know that everyone listen carefully. I want your 100% attention because it's the most important topic from the chapter. You are going to pay attention, okay? Alright. So, we know that if we provide heat energy, the temperature is going to rise, right? If you provide the heat energy, the temperature will rise. And if we are providing heat energy to convert one state of matter into another, the temperature will be constant. The temperature will be constant when we are providing heat energy to convert the change of state of matter. Let's check it out with the animation, so play it. Alright, we know that when we provide heat energy, the temperature is going to rise, and when the change of state of matter happens, the temperature remains constant over there, right? Ice into water, solid state into liquid state, change of state of matter. So the temperature will remain the same. And again, if we provide the temperature, it will change from liquid state into gaseous state, water into water vapor, and provide the temperature. So please. Yes, if we provide the temperature again, the temperature is going to rise, and at the point when they change the state of matter from liquid into gas, water into water vapor, the temperature over there remains constant, that is 100 degrees Celsius, which is nothing but the boiling point of water. We have discussed this much in the previous session, right? Yes, we have hand rises in the beginning of the session too. Yes, so unmute him.
Muhammad Aris.
Aris, yes, Aris.
Ma'am, hello.
Hello.
Ma'am, when is the class now?
Just 15 minutes
Yes, ma'am.
ago.
15 minutes past.
Yes. Alright. So, this much we discussed in the previous session. I hope you remember this. And the heat energy provided to change the state of matter, we called that energy as the latent heat. Right? Latent heat. Now listen carefully. So, I can write over here, right? Can I write? Yes. No, it's not. No, it's not visible. No, it's not. It's okay. It's okay. It's not visible. So, in this animation, let's play it again. Okay, let's play it again. Sir, play this animation again. Yes. So, in order to change the state of matter, we have to provide the heat energy. And when we provide the heat energy, temperature is going to rise. At 0 degrees Celsius, the temperature remains constant to change the state of matter because 0 is the melting point of ice. And again, we have to change the state of matter from liquid into gas, water into water vapor because 100 degrees Celsius is the boiling point of water. Here we are going to convert the change of matter from liquid into gas. So the temperature remains constant. And yes, sir, you can remove the animation. Okay. Yes, we can remove the animation over here. And my question was, when solid melts, its temperature remains the same, right? We saw that in the animation, it remains constant at 0 degrees Celsius. Let me change the color of the pen. Yes, at 0 degrees Celsius and 100 degrees Celsius, the temperature remained constant. The temperature remained constant because at 0 degrees Celsius, ice were converting into water. And at 100 degrees Celsius, water were converting into vapor. Right? Ice was converting into water at 0 degrees Celsius and water was converting into vapor at 100 degrees Celsius. At those points, the temperature remained constant. So where does the heat energy go? We know that when we provide the heat energy, the temperature definitely going to rise. But at 0 and 100 degrees Celsius remained constant. The temperature remained constant. But where does this heat energy gone? Unmute someone say.
Abid.
Yes, Abid. Where does this heat energy gone?
The heat energy goes for changing the state from solid to liquid or liquid to gas.
Very good. The heat energy is absorbed by the particle of that matter in order to change the state of matter. In order to change from ice into water, they have to gain or absorb that temperature. They have to absorb the temperature, and that is called as the latent heat. What is the definition for latent heat? Ma'am, can we discuss the homework? Yes, we can. Sir, unmute someone for me. What was latent heat? How can we define a latent heat? We discussed that, right? You can raise your hand if you know the answer. If you know the answer, just raise your hand. Let me check how many of you remember what is latent heat. You can raise your hand, okay? Raise your hand if you know that. Ma'am, it is due to latent heat. Everyone knows the answer, right? I'm so happy. So what was latent heat? Unmute one for me, sir.
Atul.
Atul, tell me what is latent heat?
Yes, ma'am. The latent heat is absorbed by particles to change the state of the substance.
Very good. Latent heat is nothing but the heat energy which has to be supplied to change the state of substance is called as the latent heat. Okay, so this was the temperature scale, and this is the 0 degrees Celsius, and this is the 100 degrees Celsius. Okay, this is the 100 degrees Celsius. And at 0 degrees Celsius, ice will melt. And at 100 degrees Celsius, water will boil. Can you see the green ink? I'll shift it to yellow. Okay. Yes. At 100 degrees Celsius, water will boil, and at 0 degrees Celsius, ice will melt. We know that, right? And if we provide the heat energy, this is fire. Okay, this is fire. If we provide the heat energy, the temperature is going to raise. The temperature is going to raise. If we provide the heat energy, the temperature will going to raise till 0 degrees Celsius. It will raise. And at 0 degrees Celsius, the temperature will remain constant over there. And the rest of the heat energy that I am providing still will be used to convert the change of matter from ice to, let me change the color of the pen, that doesn't look good, ice into water. So rest of the energy, rest of the heat energy that I am providing will be utilized to change the state of matter from ice into water, that is nothing but solid, into liquid. Okay, and rest of the heat energy after 0 degrees Celsius, okay, right after 0 degrees Celsius, remaining heat energy that I am providing will be utilized to change the state of matter, and that specific heat energy is called as the latent heat. Is called as the latent heat. Now, after complete melting, after they completely melt, okay, after complete melting, again we are providing the heat energy, and again the temperature is going to raise from 0 degrees Celsius till 100 degrees Celsius. Till 100 degrees Celsius, again the temperature is going to raise. The temperature is going to raise again if you provide the temperature right after the completion of melting. All the ice has been completely melted into water. After that, okay, after that latent heat, the remaining heat energy that I am providing will be raising the temperature, till 100 degrees Celsius, and we know that 100 degrees Celsius is the boiling point of water. It is the boiling point of water. At 100 degrees Celsius, water starts to boil. Okay, remember that. And at 100 degrees Celsius, again the temperature stops, became constant again. What happened there? Rest of the heat energy that I am providing will be utilized to convert the change of matter or the change of state of matter from water into vapor. Water into vapor, that is nothing but a liquid into gas, and the rest of the heat energy that I am providing right after 100 degrees Celsius is called as, again, the latent heat. The heat energy will change the state of matter from water into vapor, liquid into gas, and that heat energy provided to change the state of matter is called as the latent heat. And let's reverse it. Okay, let's reverse it. Is this much clear for you? Give me a thumbs up. Give me a double thumbs up if it's so far clear. Okay. So latent heat. Let's reverse it. Okay. Let's reverse it. Now we have studied liquid into gas and solid into liquid. And liquid into gas. Now what happens if gas turns into liquid? Okay. And the temperature is at 100 degrees Celsius. In order to get them back, we don't have to heat them. We have to cool them, right? Then only they can come back. We have to decrease the temperature. We have to cool them. We have to freeze the ice, right? Freeze into ice. So what we have to do? We have to cool it. We have to lower the temperature. We are going to reverse it, okay? Now listen carefully. We are going to reverse it, okay? So the temperature is at 100 degrees Celsius now. What are we going to do? Yeah, the temperature carries out like that, okay? So the temperature is here now. Let me erase it, okay? Okay. Wait for a second, okay? Yes, here we go. Imagine our temperature over here, okay? Our temperature is over here, okay? Above 100 degrees Celsius, it is in water vapor. It is in gaseous state, so the temperature is over here. So in order to get the liquid back, that is gas into liquid, okay, vapor into water, water vapor into water, water vapor into water. This is exactly what we are going to do now. So the temperature is over here. In order to get the liquid back, we have to lower the temperature. In order to lower the temperature, what will we do? We will cool it. When we cool it, the temperature will get lower. The temperature will lower. At 100 degrees Celsius, it remains constant. Okay, as we said earlier, at 100 degrees Celsius, it will remain the same. When they reach 100 degrees Celsius, it will remain the same, and all the gas particle will again convert into liquid state. Water vapor will be converting into water state. After the completion of all the vapor into water, after completing the condensation, it is called as a condensation, right? Vapor into water, gas into liquid was called as a condensation. After all the condensation, after all the water vapor converted into water, again if we cool, the temperature is going to lower. So at 100 degrees Celsius, the remaining heat energy, the remaining cooling energy that we provided will be utilized to change the state of matter from gas into liquid. So at 100 degrees Celsius, they are going to remain the same, and the energy that we are still providing will be utilized to change the state of matter from gas into liquid. That is exactly the latent heat. That is exactly called as the latent heat. After all the completion of condensation, again the temperature is going to lower. And they will reach 0 degrees Celsius. We are keep on decreasing the temperature. They will reach at the point 0 degrees Celsius. At 0 degrees Celsius, we know that it is the freezing point of water. 0 degrees Celsius is the freezing point of water, where water will convert into ice, liquid into solid. Water will convert into ice at 0 degrees Celsius, and the energy, the external energy that we are providing will be utilized to convert the change of matter from liquid into solid, and that heat energy is called as the latent heat. And if we again lower the temperature, after the completion of complete freezing, the temperature is again going to lower. So at the point of 0 degrees Celsius and 100 degrees Celsius, they will become constant. Just because the heat energy, rest of the heat energy that is providing will be utilized to change the state of matter. That is nothing but latent heat. Is the latent heat clear for you? Anyone have any doubt regarding this? Do anyone have any doubts? No doubts. Shall I move forward then? New students, are you able to follow this? Yes, right? Give me a double thumbs up if everything is clear so far. Yes, very good. Now latent heat is so much clear, right?
Niranjan Rajit has a doubt.
Niranjan, do you have any doubt?
Will you please hand raise?
Or if you can ask that in the comment box, that will be better.
Oh, okay.
Yeah, that will be better if you can ask the questions in the comment box. Okay, I can still say it. All right. Alright, so latent heat is over. Now we have to study the latent heat of fusion. That was the common term, latent heat. Okay, please don't write it down. Okay, I will give time. Listen to me first. Okay, I will give time to write it down. So the latent heat was a common term for everything. So wait for a second. I'll give time to write. Okay, listen to me now. So the latent heat. Who is still writing, ma'am? Who is that?
This one?
No.
Abid.
Oh, yes. I told you, listen to me. I'll give time to write. Right? So you won't get the concept if you just keep on writing like that. You will not get the point. So latent heat was the common term. Now we have to study latent heat of fusion and latent heat of vaporization. Now tell me, what is fusion? What is fusion? What's the other name that you can give for fusion? Comment it. What's the other name that you can give for fusion? Is that boiling? Is fusion refers to boiling?
No, teacher. It's
Oh, we have the answer. So very good, very good. That is nothing but melting. Ma'am, unmute one for me.
okay. Let's unmute. Rahan.
Rahan. Rahan,
Yes, ma'am.
what was melting?
Melting is the changing of solid into liquid.
Solid into liquid. Solid into liquid was called as melting. Solid into liquid is melting. Now listen to me. We know what is latent heat, right? We know latent heat. So the amount of heat energy required to change 1 kilogram of solid into liquid at atmospheric pressure without any change in the temperature at its melting point is called as latent heat of fusion. Okay, I have just read the definition. Now listen to me carefully. I have 1 kilogram of ice. I have 1 kilogram of ice. Okay, 1 kilogram of ice. I have to convert this 1 kilogram of ice into 1 kilogram of water. Into 1 kg of water. Okay, I have to convert 1 kilogram of ice into 1 kilogram of water. So what I have to do? I have to raise the temperature. I have to provide the heat energy. Now I am going to provide the heat energy. And we know that at 0 degrees Celsius, the ice is going to melt. And we know the latent heat, right? The energy that is providing right after 0 degrees Celsius, and the 0 degrees Celsius will remain constant, right? That is nothing but without any change in the temperature. Without any change in 0 degrees Celsius. 0 degrees Celsius will be remaining constant during this process. 0 degrees Celsius is never going to change during the conversion of state of matter. So without any change in the temperature at its melting point. So melting point is nothing but 0 degrees Celsius. Without any change in the 0 degrees Celsius, they are going to melt. And the heat energy that is provided to convert the 1 kilogram of ice into corresponding water without changing the temperature is called as a latent heat of fusion. And there is another thing at atmospheric pressure. At atmospheric pressure, we are not going to increase the pressure, we are not going to decrease the pressure. At atmospheric pressure, there is nothing but 1 atm. 1 atm is the atmospheric pressure at the sea level. At sea level, 1 atm is the atmospheric pressure. Without any alteration in the atmospheric pressure and without any alteration in its melting point, the heat energy required to change 1 kilogram of solid into liquid is called as latent heat of fusion. It's called as latent heat of fusion or latent heat of melting. Latent heat of melting or latent heat of fusion. Yes, is that clear? Yes, Abid. Ma'am, unmute us. Abid.
Yeah. Yes, Adit.
Yes, unmute. Quickly unmute. We are lacking the time. Not able to unmute? You don't have any questions to ask? No questions.
You are not getting any. Oh, yes,
No questions. So clear so far? Quickly write down the definition. Quickly write down. Ma'am, can you please zoom it? Zoom the camera. Okay. I'm not able to see it.
Okay, I will read. Ma'am, for us,
Ah.
the chapter coming in exam is chapter 2, is
Matter around a spirit.
Only that, not even full chapter of it, we learned till Tyndall effect.
Tyndall effect, alright.
both
That
the
is second
functions.
chapter, is matter around a sphere. We'll discuss that chapter right after this chapter, okay? Right after this chapter, we are going to learn that chapter. Yes, ma'am, unmute him.
Yes, Rupan.
Rupan, yes, Rupan. Do you have any concern or doubt?
Yes, ma'am.
Yes.
Ma'am, my computer just got like it got shut down. Ma'am, can you explain what were you explaining before? Like 5 or 2 minutes ago.
That was nothing but latent heat diffusion. That's the one that I was discussing. Did you came late? Did you came late?
No, I joined on time, but like my computer had some problem. So
Right.
shut down.
Anyway, there's a YouTube live going over there, so you can re-watch it again, okay? If you wish to watch it again, you can, okay? No worries. Alright. And there.
Aris,
Aris, yes, Aris.
can we write now? Is that the concern?
Rest of your students, quickly write it, okay?
Ma'am.
Quickly write it down. I'm going to
Ma'am.
change the slide. Yes, Aris.
Ma'am, I don't have doubt regarding this, but I have doubt about some other topics.
Okay.
Ma'am, you thought that melting point of ice is 273.16, right?
What was that?
You thought that melting point is 273.16, right?
273.16 Kelvin or 0 degrees Celsius. It's one and the same.
But in the textbook it's written 273.15.
It's one and the same, okay? 16 and 15 is almost similar, right? Some of they given like 16 and 15. It's both of them are correct, okay?
Okay.
Alright. So quickly write it down. If you're done with the writing, give me a thumbs up, okay? Give me a thumbs up. Yes, if you want more time to write it down, you can take a screenshot. Ta-da! You can take a screenshot, okay? If you want, you can take a screenshot and we'll move forward. We have so much things to study. Yes. Shall I then? Shall I?
Yes, we got lot
Yes.
of thumbs up.
A lot of thumbs ups.
No, somebody is asking.
So quickly take pause. Pause. Quickly take a screenshot, okay? Quickly take a screenshot. Is there anyone who is not paying attention to the class? You can just raise a hand. Raise your hand.
No, but
Everyone is paying attention. Very good. Mas.
that will be.
Mas. I know that you will raise your hand. I know that, Mas. Anyway, you are paying attention.
That's why you heard.
Yeah. Yes. Shall I move forward? Yes. Quickly take a screenshot and take a screenshot. Take a screenshot. In 3, 2, and 1. Here we go. Yes. So the next one is latent heat of vaporization. Latent heat of vaporization. It's just the same as fusion. Okay, just same as fusion. Just change the state of matter from liquid into gas. It's one and the same. Okay, if you just study latent heat of fusion, you can easily write what is latent heat of vaporization. It's one and the same. Only the terms are changing. For example, I have 1 kilogram of water. 1 kilogram of water. I have to convert them into 1 kilogram of vapor. Okay. So what I have to do? I have to raise the temperature. Here we go with the 0 degrees Celsius and thus the 100 degrees Celsius. So we have to raise the temperature in order to convert the change of matter. So we will raise the temperature. When they reach 100 degrees Celsius, the temperature will remain constant without altering the 100 degrees Celsius. The energy required to change the state of matter from liquid into gas is called as a latent heat of vaporization, and without altering 100 degrees Celsius and without altering 1 atm pressure, the temperature or the amount of energy required to change the state of matter from 1 kilogram of liquid into gas
Some
is
of them
called
are
as-
like 1 kilogram liquid.
Yeah, it's It's a common term. Okay,
Then
someone is saying,
also-
how can we weigh 1 kilogram of liquid, man? Alright.
It's possible.
That's possible, okay? That's possible. Yeah, we can always refer 1 kilogram or 1 liter. It's same. Yes. Ma'am.
Yes.
No, someone is like, no ma'am, it won't reach its melting point. Huh? Melting point? Have to. Yeah, it's a boiling point. I'm sorry, really sorry for that. It's boiling point. It's boiling point. Okay.
Still, they are like, did you mean like kiloliter?
No, kilogram. Okay, we can always mention them in kilogram or liters. It's same. Temperature at its boiling point. Okay, don't get confused. It's boiling point. It's boiling point. Okay, boiling point. That is nothing but latent heat of vaporization. Yes. It's same, right? It's one and the same with the fusion, latent heat of vaporization and latent heat of fusion, and we have latent heat of condensation. You have to study that. Latent heat of freezing, it's all one and the same. The amount of heat energy to change 1 kilogram. Okay, don't forget 1 kilogram. 1 kilogram is very much important. 1 kilogram, okay? In order to change 1 kilogram of substance, it's called as the latent heat of vaporization or latent heat of fusion or latent heat of condensation or latent heat of freezing. Alright, it's all one and the same. But don't ever forget to mention 1 kilogram and at same atmospheric pressure and without altering its boiling point. That is latent heat. Specifically talking about the change of state of matter. I hope that was clear. Now my question. Now again the question. Yeah. Let me ask the question, okay? It's question time. So, let me change the color of the pen. Dude. Okay. Now my question is, water at 0 degrees Celsius or ice at 0 degrees Celsius will be having more energy. Which one will be having more energy? Water at 0 degrees Celsius or ice at 0 degrees Celsius? You can raise your hand if you know the answer. If you know the answer, you can raise your hand.
One comment is like, ma'am, if it is 2 kg, what will we say?
2 kg?
1 kg, if it's 2 kg, how can?
2 latent heat of vaporization. Or latent heat of vaporization square.
No, ma'am, they will think that was right.
No, okay, I was joking. Don't take it serious. I was just joking, okay? It always refers to the 1 kilogram, okay? It always refers to the 1 kilogram. Don't ever write 2 kilogram. I was just joking. Alright. Alright, do you know the answer? Water at 0 degrees Celsius or ice at 0 degrees Celsius will be having more energy? Yes, ma'am. Unmute one for me.
Yes, let's.
There
are a lot of hand raises.
Lots of hand raises. Our ma'am is still confused with those hand raises.
Unmute Sri Lakshmi.
Sri Lakshmi have the beautiful background behind her.
Yes, ma'am.
Yes, Sri Lakshmi. What's the answer?
Yeah, water at 0 degrees Celsius.
Water.
Because water has latent heat.
Very good.
When the ice converts to water, the water will absorb the liquid.
Very good. Water at 0 degrees Celsius will be having more energy because the water absorbed all the heat energy, right? Absorbed all the heat energy during the state of matter, during the conversion of state of matter. So water at 0 degrees Celsius will be having more energy. So which one will be more cold? Water at 0 degrees Celsius or ice at 0 degrees Celsius is more colder? Yes, tell me. Do we have the answers in the comment box?
Yes, we have.
Yes, we have, right? Very good. And they are all goes towards the ice, right?
No, some of them are to water.
No, ice. So the first one, more energy will be going to water and coldness will always goes to the ice. Okay, so ice will be more colder than the water at 0 degrees Celsius. Okay, at 0 degrees Celsius, ice will be more colder than the water because ice at 0 degrees Celsius. Okay, it is absorbing more heat energy to convert into water. So water will be more hotter because it is absorbing all the heat energy, right? The water, not to convert the water, is absorbing all the heat energy. So water will be much hotter than the ice. So ice will be colder at 0 degrees Celsius than the water at 0 degrees Celsius. But the water will be having more energy. Okay, more energy will be having water and more hotter will be also water. Okay, and again I have another question. Okay, so if we burn with the water at 100 degrees Celsius or steam at 100 degrees Celsius. Okay, steam at 100 degrees Celsius or water at 100 degrees Celsius will be having more energy. Which one will be having more energy? The water at 100 degrees Celsius or steam at 100 degrees Celsius will be having more heat energy. Ma'am, unmute one. Samuel. The water at 100 degrees Celsius or steam at 100 degrees Celsius will be having more energy. Steam at 100 degrees Celsius will be more energetic. Why? Samuel, why?
Yes, we can.
Yes, ma'am. But that's because heat was observed during state of conversion from liquid to vapor.
Yes, so very good. The steam is absorbing more energy, more heat energy. So the steam will be having more energy. Which one will be more hotter? The steam or the water? Ma'am, unmute someone else.
Okay.
Which one will be more hotter, steam or water?
Let's unmute Neha.
Neha, which one will be more hotter? The steam at 100 degrees Celsius or water at 100 degrees Celsius?
Steam.
Steam at 100 degrees Celsius. So very good, Neha.
Ma'am, also I have a doubt.
Yes.
So, can't you say ice at 0 degree Celsius also has more energy, because you told that latent heat works in both ways, like while you convert water into ice or you convert ice into water. So, in case you are converting liquid into solid, won't ice have more energy in that way?
No. Because we know that in solid state they will be having lesser energy, right? Because the particles are close to each other and also we are lowering the energy, right? We are lowering the heat energy, we are cooling them. So the energy provided will be lesser. We are making them together, right? We are making them close to each other. So the energy will be decreased, right? Then only we can make liquid into solid, right? Am I right?
Yeah.
We are going to reverse it, right? Because we are lowering the energy. The heat energy is lowering. We are cooling them. So obviously the energy will be lost. And we know that solid will be having lesser energy than the liquid, right? Yes, alright. So the heat energy, the burn caused by the steam will be, the questions may ask like that, okay? The burn caused by steam or water will be more severe. So the burn caused by steam will be more severe. Okay, you have to keep that in mind. Burn caused by steam will be more severe than the water. Okay, if we pour boiled water on your hand, it will be less severe than the steam. Okay, steam at 100 degrees Celsius will be having more energy. So the burn caused.
ma'am.
Eh?
They're like, how is it, ma'am?
How is it, ma'am?
Yeah.
So I have told you.
You already, yes.
I have already explained it, right? So Steam at 100 degrees Celsius is more hotter. It's more hotter than the water at 100 degrees Celsius because we are providing the heat energy. That heat energy is not raising the temperature. All the heat energy is utilized by the steam. Okay, all the heat energy is absorbed by the steam. So steam is more hotter than the water. So the burn caused by steam is more severe, right? Yes, doesn't care about the temperature. Still, they have both of them will be having same temperature, but the heat energy will be different in both of them. Steam will be having more heat energy than the water. So the burns caused by steam will be more severe. Okay. So give me a thumbs up if so far it's clear for you. If so far it's clear, give me a thumbs up. Give me a thumbs up if it's so far clear. We are going to discuss about the effect of change of pressure. Yes. Alright. Effect of change of pressure. We know that likewise temperature. The temperature is changing, right? The temperature is affecting the conversion of state of matter. Temperature is affecting the state of matter. Likewise, pressure is also affecting. Pressure is also affecting. We have already learned that. So, can we play the animation? Yes. Okay. Yes, let's have an animation. Okay, yes, sir. Let's take a syringe. I have a syringe over here, okay? Watch it carefully, okay? Is everyone paying attention over here? Clap, clap. Here. Yes. Very good. So, I have a syringe over here and I'm going to fill the syringe with air. Okay, I'm going to fill this. No, sir. Alright. I'm going to fill this syringe with the air. Okay, let's fill it. Yes, sir. Let's fill it. Yes, let's fill it. So we have the gas inside this syringe. You can see that, right? We filled the air by pulling out the syringe, okay? So we have the gas inside the syringe and we close the cap because the gas may escape. So we don't want the escaping of gas. So we just close the nip, okay? We just close the nip and we have gas inside the syringe. And now what do you think will happen if I press the syringe? What will happen if I press the syringe? Ma'am, unmute one for me.
Okay.
You already saw that. Alright, anyway, let's ask.
Yes, Suhail.
What happens if I press this? What
Yes,
property
ma'am.
of gas it is?
If we close the syringe, it will create a pressure which is unavailable to press it completely.
Alright, what property of gas shown over here?
Gas.
What property
Air.
of gas?
Air.
Air?
Yeah.
What property of gas?
Property. Oh, molecules.
Oh, atoms!
Mm-hmm.
What property? We have discussed the properties of the gases, liquids and solids, right?
Let's ask someone else.
Yes, let's go for someone else.
Let's ask Abid.
Abid.
It's like me.
Yes, Abid.
Me.
Is that molecules, atoms, air? What is the answer that he told? No, air, gas, molecules. That's it. What kind of
Gas occupies space.
gas occupies space? Definitely. I'm going to press this. So, what kind of property is that?
Compressibility.
Compressibility. Very good. We can compress the gas. Who was that, man?
Which one?
Before we unmuted someone, right?
Okay.
Who was that?
Zuhair.
Zuhair, did you get it now? Nod your head if yes. It is compressibility. We are compressing it, right? The gases are highly compressible. The gases are highly compressible. That is why we are compressing them in the cylinder. So this property shows the compressibility of gases. Yes, sir, you can play. Now we can compress the gas, right? Let's close it and let's compress it. We are compressing. The gases are highly compressible. The large amount of gas can be compressed in the small area because they have large space in between the particle. Do you want me to repeat this animation again? Yes, let's do it again, sir. Yes. So let's plug the air in. Let's take the air in. Okay, let's plug it in. Here we go. And cabin and compress it. That is compressibility. So if we apply the pressure, the gases can be compressed. Okay, the gases can be compressed if we apply some pressure. Okay, if we apply some pressure, the gases can convert into what? The gas can be converted into liquid. Ta-da! The gases can be converted into liquid at a high pressure. So if you take the gas inside the syringe and if you just press it and tell me like, ma'am, the gas is not converting into liquid, you cannot see that, okay? We have to apply a high pressure. We cannot apply that by using our hand, okay? It cannot be converted into liquid. Don't ever try it in your home and don't blame me, okay? Don't do that in your home and don't blame me if you just compress it, or like John is like over there is compressing the gas inside a sand and looking into the hand. Ma'am, it is not converted into liquid. I applied pressure and I compressed it. It doesn't turn into liquid. It's not like that. Okay, it's not like that. We have to apply a large amount of energy or pressure in order to convert. Okay, we have to apply a large pressure in order to convert. Okay, we cannot do that in the syringe or in your hand. You cannot do that. Okay, it's just a simple explanation.
They all are like, what if we are strong enough?
What, we are strong enough like the Hulk? No, you cannot do that. Even Hulk cannot convert the gas into liquid by using his hand. No, never. Okay, we have to compress it by high pressure. You cannot even imagine that. High pressure should be there.
Pressure condition. Like,
yes. We have so many atmospheric conditions. We have to apply high pressure. Otherwise, we cannot convert them. In applying pressure, we can convert gas into liquid. That was the point. Pressure. So by applying pressure, we can convert gas into liquid. The next animation, sir. Yes, the next one over here. Okay, let's compress the liquid. Okay, let's compress the liquid. Let's check what will happen. Yes, sir. Let's take the water in and let's try to compress it. Close the lid, otherwise the water will go away. So just compress it. Try to compress it. Everyone, take your hand and compress it. Yes, try to compress it. I cannot do that. I'm not able to compress it. Why? Why can't I compress the liquid? Everyone is clapping their hands now. Now I'm told you to clap. You have to act. You are good actors, right? You have to act. I cannot compress it. Act. Acting should be coming out from your face. It is not compressing. Yeah, everyone is literally acting. Very good. You are all good actors. Very good. The water cannot be compressed by using our hand. Okay, it is not compressed in our hand. But in high pressure, we can compress them. Okay, so we cannot compress in the normal conditions. We cannot compress the liquid. In normal condition, we cannot compress the liquid, but when we apply a high pressure, again the liquid can be compressed. By applying the pressure, the liquid can be converted into solid. Liquid can be converted into solid. Okay, so that's the point. On applying pressure, the gas can be converted into liquid and the liquid can be converted into solid, not just the syringe. Okay, so this the property shows that liquids are not compressible at normal conditions. The liquids are almost incompressible. They are almost incompressible at normal conditions, but at a higher pressure, if we apply high pressure and compress the liquid, the particles will come close to each other and we can convert them into solid. You can remove this animation, sir. And let me show that by using an image. Here we go. We have gas and the particles are far away from each other, right? The particles are far away from each other, as you can see over there. The particles are far away from each other, and when we press it, when we apply pressure, the particles will come close together. and they can convert into a liquid. The particles can come close together. If you just compress it again, if we are going to compress it again, the particles will again come closer and convert into solid. So on applying pressure, we can just convert the change of matter from gas into liquid and liquid into solid. Okay, that was the effect of pressure. Yes, that was clear, right? Yes, ma'am. Unmute someone who's raising their hands. Yes.
Abhineet.
Yes, Abhineet. Do you have any doubt?
Yes, ma'am, this was like, since this, what do you say, gas is highly compressible, can gas actually like kind of change into liquid? Because liquid molecules will be like more closely packed than gas, right? So when you compress it, the molecules.
Definitely, that is what I was explaining, right? That is exactly what I was explaining. If we apply the pressure, the particles will come close together and they can convert into liquid. Yes, definitely. At high pressure, gas is going to convert into liquid, liquid is going to convert into solid.
Okay.
Alright. So,
Yes, also
At-
Abid.
yes ma'am, unmute them.
Yes, Abid.
Yes,
Hmm.
yes, the solids are not compressible.
Yes.
In this,
Solids
in this-
cannot be compressed again, right? The solids are incompressible. We have learned that.
but then
solids-
why you showing it's more compressible?
It is not compressible. Do you want me to show that? Yes, I have a live experiment over here. I have the pen. It's a solid, and I try to compress it. No, I cannot compress it. The live experiment. Ta-da! Enough? Yes, if you try to break a stone, we cannot do that, right? Okay, if we have a stone in my hand and I try to compress it, the stone cannot
Actually,
go
we
into
already discussed about the case of sponge and things.
Ah,
in the
yes,
class,
right. We
but
already
again-
discussed that in the previous sessions too.
No,
Discussed
ma'am.
about everything, right? We already
No.
discussed about the compressibility of everything. Now I'm talking about pressure. That is why I'm repeating those things again. So always remember, at a high pressure and low temperature, we can convert gas into liquid. We can convert gas into liquid and liquid into solid at high pressure and low temperature. Keep that in mind. We had to lower the temperature, right? We already learned that. If we lower the temperature, the gas is converting into liquid, liquid will convert into solid, freezing, right? So we have to lower the temperature. At low temperature and high pressure, we can just convert them. Condensation and freezing, we learned that. So keep that in mind. Moving forward. Shall I move forward? Yes, and if you have any queries, drop it in the comment box. Okay? I'm repeatedly telling this. If you have any doubts, drop it in the comment box. We have a supporting teacher, Arya ma'am is very waiting for the comments. Okay? She's really waiting for the questions to answer it. Alright. So give her some questions. Okay? Alright. So at the previous session I made a mistake, I guess. I have told like as the height goes, the pressure increases, but I was wrong. So I just mistakenly told that. Okay. So when the height increases, the pressure lowers. Okay, the pressure lowers. Pressure lowers when the height increases. So at the sea level, this is the sea level, right? This is the sea level. At sea level, the temperature or the atmospheric pressure, okay, the atmospheric pressure is 1 atm. So 1 atm is the pressure. 1 atm is the pressure. Okay, at sea level, 1 atm is the pressure. Keep that in mind. Okay, 1 atm is the pressure. And the unit of pressure is nothing but PA, Pascal. Pascal. Okay, Pascal is the SI unit. Okay, SI unit of pressure. Write it down. Quickly write it down. At sea level, pressure is 1 atm and SI unit of pressure is Pascal, PA. Pascal. Okay, Pascal. Okay, it's not Rascal, it is Pascal. Okay, keep that in mind. Alright, Pascal is the SI unit of pressure and 1 atm is the pressure at sea level. At sea level, 1 atm is the pressure, atmospheric pressure. I hope you know what is atmospheric pressure. So atmospheric pressure is nothing but the pressure exerted by the air. Okay, it's the pressure exerted by the air. It is the atmospheric pressure, and it is 1 atm at the sea level, and the SI unit of pressure is Pascal. Keep this in mind. Now listen to me carefully. As the height increases, the pressure decreases. So at the mountain region or the hill region, the pressure will be low. Okay, at the hilly regions or at the hill stations, lower pressure will be there. And there is an important concept that you have to study, that is, when we increase the pressure, the boiling point is also going to increase. Okay, so as the pressure, write it down, okay, as the pressure increases, boiling point will also increase. There is an important concept that we have to study over here. Okay, there is an important concept. You have to learn it, okay? You have to keep this in mind. As the pressure increases, boiling point also increases. What is boiling point? Temperature required to change the state of matter from liquid into gas is the boiling point. Temperature required is called as the boiling point, right? Liquid into gas. And the temperature required to change the state of matter from liquid into gas is called as the boiling point. So as the pressure increases, boiling point also increases. It is inversely proportional. Okay, it is inversely proportional. So just always remember that if we lower the pressure, the boiling point also lowers. If we increase the pressure, boiling point also increases. Okay, it's just opposite to each other. If we lower the pressure, boiling point also lower. If we increase the pressure, boiling point also increases. Now pay attention. Everyone, pay attention over here. At the hill station, we know that we have a lower pressure. So, is the boiling point increases or decreases? Ma'am, unmute one for me.
Okay, let's unmute. Yes, Abdullah.
Who's that?
Wait, ma'am. Abdullah,
I am. Yes, I am.
Yes, ma'am.
I am.
As the pressure increases, the boiling point increases. So if the pressure decreases, the boiling point decreases.
Yes, what's the boiling point of water now?
Boiling point of water is this one, 0 degrees. No, that's right. That's 100 degrees.
Boiling point is 100 degrees Celsius. 100 degrees Celsius, the boiling point. So tell me, at a hilly station or hill stations or at the mountains, is the boiling point is higher than 100 degrees Celsius or lower than 100 degrees Celsius?
It's lower than 100 degrees.
Lower than 100 degrees
because
Celsius.
The higher you go, the lesser the pressure.
Very good. When we go higher, the pressure is decreases, and likewise the boiling point also decreases. So boiling point of water in the mountains or hill stations are lower than the 100 degrees Celsius. Okay, it will be lower than the 100 degrees Celsius, not exactly the 100 degrees Celsius. 100 degrees Celsius is at the sea level. So 100 degrees Celsius, the boiling point of water at the sea level, at 1 atmospheric pressure is 100 degrees Celsius. You have to keep that in mind. And as we go up, pressure decreases, likewise boiling point decreases. There is an important application over there. So, you may be heard about that. At hill stations or mountains, food cook slower. Have you ever heard that? The food cooks slower. And now can you tell me why? The food cooks slower in the hill stations or in the mountain regions. Is that your first knowledge? Really, ma'am? Is the food cooked slower in the hill regions or in the mountains? Was that your first knowledge? Or are you hearing that for the first time? No, right? You have heard it. The food cooks slower in the mountain regions or in the hill stations. Why? Ma'am, can you please unmute one for me?
Okay.
Why it is lower?
Rishikesh.
Why it is slower? Rishikesh, can you guess why? Rishikesh.
Why it is slower? The pressure it will decrease.
Pressure is decreasing, boiling point also decreases. Why it will cook slower? That is my question.
Why the cooks slower?
Cook slower, yes. Cook
100
slower.
degree, 100 degree Celsius, it will be lower.
The boiling point is lower than the 100 degrees Celsius. Yes, definitely.
Then the food cooks slower, it will be less compressible.
No worries. I want Mas. Where's Mas? Mas was expert in this chapter, right? Mas was very expert in this chapter. Mas, where are you? Raise your hand. Mas, raise your hand. Mas was like, oh my god. Yes, Mas. Now answer me.
This chapter.
Yes.
This chapter.
You told me in the beginning, right? You were expert in this chapter. Now answer me.
This chapter.
No. There's a YouTube live. There's a proof going over there.
I can rewrite the proof.
You cannot rewrite the proof. Just tell me the answer. You was expert in this chapter. You told me that, right? You told me like, ma'am, let's end this chapter. I'm already expert in this chapter. Let's go back to the next chapter, right? You had told me that. And you're like, ma'am, I don't know the answer. How is it possible? If you're expert in this, you must know the answer.
What's the question?
What was the question? In the mountain regions, food cooks slower. Why?
Hola.
Yes, food.
In the mountain regions.
Food cooks slower.
Ajay. I think so.
Alright. Okay, you're not an expert in this chapter. I got it.
The answer is the air pressure.
No. Yes, ma'am.
No,
Mute him.
the-
You're not an
the
expert in
air
this chapter. I win.
the
Alright.
air pressure at like higher altitudes. You can say.
No,
I
ma'am.
think
You can mute him, ma'am.
I can accept that you want.
No, your chance is over. Your chance is over. It's done. It's done. So the answer is, we know that at lower pressure, the boiling point will be lower, right? So if we boil the thing, okay, we are boiling the foods in the water, right? Yes, we are boiling it. And when we boil it, the water will boil faster because the boiling point is less than 100 degrees Celsius. The boiling point is lesser than 100 degrees Celsius. So it boils faster. What happens if they boil faster? Before the food cooks, all the water will convert into vapor, right? Am I right? Before reaching the cooking time, it will just vaporize. So the boiling point will be lesser than 100 degrees Celsius. So it will boil faster. They will boil faster. So that what happens? So that the food will not cook so fastly. So they require more heat energy, right? So the food cooks slower in the mountain region. Was that clear? Was that clear, Mas? Yes, very good. Was that clear for everyone? Was that clear for everyone? So before it cooks, it reaches the boiling point and the water will just convert into vapors. Water will just convert into vapors. So the food cooks slower in the mountain regions. Now I have another question. What happens in the pressure cooker? We have the pressure cooker, right? Will the food cooks faster in the pressure cooker or slower in the pressure cooker? We have pressure cooker. Pressure cooker. What happens in the pressure cooker? The food, it is cooking faster or slower? Is it cooking faster or slower?
Ma'am, there's a request to
Yes.
repeat again this part.
Yes, I will.
Okay.
So in pressure cooker, the food cooks faster. Okay, I'm going to repeat this part again. Okay, I'm going to repeat that part again. So as we go up, we know that. Listen carefully. Okay, listen now carefully. So as we go up, the pressure decreases. We know that as the pressure decreases, the boiling point of water also decreases. And we know that the boiling point is 100 degrees Celsius where they boil, where they start to boil and convert into vapor state. And what happens if the boiling point decreases? For example, if it is 92 degrees Celsius, if it is 92 degrees Celsius, okay, lower to 92 degrees Celsius. And when the heat energy or the temperature reaches to 92 degrees Celsius, the heat energy is just lower than 100 degrees Celsius. Am I right? The temperature is lower. The temperature is just lower. So the heat energy is lower then. That means the food cooks slower over there because the temperature is not enough to cook it faster. And also at 92 degrees Celsius, the water is just going to convert into vapor. The water just convert into vapor, so it will not get enough time to cook those vegetables or meat. So the food cooks slower at the hill region where the temperature where the pressure is lower and the boiling point is also lower. So before reaching 100 degrees Celsius, the water is going to boil and going to convert into vapor. Okay, they are not getting enough heat energy. They are not getting enough heat energy or temperature to cook those things. So the 92 and 100 degrees Celsius is a large difference, right? It's a large difference. So that is why the food cooks slower in the hill regions or in the mountains. Now we're talking about the pressure cooker. Talking about the pressure cooker. Okay, talking about the pressure cooker. In pressure cooker, we are applying the pressure and we are closing it, right? We are closing it. So pressure inside the cooker will be higher. The pressure inside the cooker is higher than the outside. Am I right? Am I right or wrong? Yes, the pressure inside the pressure cooker will be higher than the outside. So what happens now? We know that as the pressure increases, boiling point will also increases. As the pressure increases, boiling point also increases. Now tell me, water boils at 100 degrees Celsius. I'm talking about the pressure cooker, okay? I'm talking about the pressure cooker. Will it boil at 100 degrees Celsius or above 100 degrees Celsius or below 100 degrees Celsius? Yes, tell me in the comment box. Tell me in the comment box. Will the boiling point remain the same as 100 degrees Celsius or above 100 degrees Celsius or below 100 degrees Celsius? Yes. Quickly answer me. Quickly answer me. Everyone is like below.
Someone is above 100 degrees Celsius, someone is below.
So, whomever who is telling below has not got the concept. It is higher. We know that as the pressure increases, boiling point also increases. In pressure cooker, the pressure is increasing. So the boiling point also increases, right? So the boiling point will be higher than the 100 degrees Celsius. It will be higher than the 100 degrees Celsius, not below. As the pressure decreases, boiling point decreases. That was the case in mountain regions. That was the case in mountain regions. Now it is not the case. The pressure is increasing. Boiling point also increases. So it is above 100 degrees Celsius. And we know that after 100 degrees Celsius, the water was not boiling in the pressure cooker because 100 degrees Celsius is not the boiling point of water inside the pressure cooker because it will be having a higher pressure. So when they reach 100 degrees Celsius, water is not going to boil. The water is not going to boil. So it needs more temperature. It needs more heat energy to reach the boiling point. At that time, they will be needing more energy. That means they are absorbing more heat energy. That means the food cooks faster in the pressure cooker because they will be having enough heat energy to cook those foods. So in pressure cooker, the meats or the vegetables will cook faster just because the boiling point of water is higher than the 100 degrees Celsius. Okay. Is that clear now? Is that clear now? Give me a thumbs up if it's clear. Give me a thumbs up if it's clear. Everyone. It's clear, right? I will ask the questions in the next class. If you don't answer, definitely I'll give the punishments. You remember that, right? Yes, I'm expert in giving the punishments. So don't ever forget that. I'm definitely going to punishment and give the punishment. So if you have any doubt, just ask me right now.
Is the hand raises or doubts or concerns?
I'll move forward in 5. Okay, in the count of 5, I'll move forward. Within that, you have to raise the hand if you have doubt.
Yes, Abhineet Pradeep has a doubt.
Who's that?
Yes, Abhineet.
Abhineet. Yes, Abhineet.
Mom, you said that food in pressure cooker, if you keep it, it will boil faster.
No, it will boil slower. It will boil slower. It takes time to boil. So at the time when they reach the boil, they have enough time to cook that, right?
Yeah.
Yeah, that's why they are cooking faster. Do you get it?
Okay.
Not actually, right?
Why is water required to cook food? In that cases only.
Yeah, I'm only talking about the water, okay? Water. Not like a meat, cooking alone. I'm not talking about that. I'm talking about the water.
Okay.
Yes. So, always remember, if the pressure increases, boiling point increases. If the boiling point increases than the 100 degrees Celsius, it needs time to reach this point. For example, it requires 109 degrees Celsius, 109 degrees Celsius. In order to reach 109 degrees Celsius, it needs more time than the 100, right? It needs more time. At the time when they reach 109 degrees Celsius, they can just boil. We have enough time to boil. But that is not in the case of mountain region. The boiling point is lower. So they lower the time. So that is why food is cooking slower in the mountain region, and in the pressure cooker they cook faster because we have high pressure. And all the concept was, as the pressure increases, boiling point increases. That's it. That's the core point. If you don't remember all these things, just forget it. But the core point is this. As the pressure increases, boiling point also increases. These are some daily life explanations or daily life applications. If someone is asking like why food cooks faster in the pressure cooker, you have to give this explanation. Okay? And when you go for a picnic in the mountain region and someone asking you like why it is taking so long to cook, you have to explain this phenomenon to your parents. Mom, it is like this. Don't be panicked or don't be angry with that. This is the process that's happening over there. You have to explain this. As a chemistry student, that's your responsibility to answer these things. So, these kind of questions, right? Yes. I hope no one else have any doubts. We'll move forward.
Atul or Abid have any doubt?
No.
Atul, Abid.
No, right.
Okay,
Yes.
Somebody's like, how did you get 92 degrees Celsius?
Yeah, that was just assuming, okay? I was just assumed it. 92 and 109, I just assumed it, okay? It's not the exact points. I just assumed it. Alright, now the next thing that we have to study is evaporation detailing. We already know what is evaporation, right? Ma'am, unmute one for me.
Okay, so let's unmute Anika.
Aneka, what was evaporation?
Anika Jacob Robin.
Aneka Jacob, what was evaporation?
Can you hear me?
Yes, I can.
The change of state of
Matter from?
state of matter from a liquid state to a gaseous state.
At what point?
Liquid state to a gaseous state below the boiling point.
Below the boiling point. Very good. So at the boiling point, it is called as a boiling. The boiling and evaporation are different, okay? So the conversion of state of matter from liquid state into gaseous state below its boiling point is called as evaporation. We detailedly discussed about that. So I'm not going to repeat this again, okay? I'm going to repeat this again because we detailedly discussed about this. The difference between the evaporation and boiling, right? Do you want me to repeat that again? Really, we lost the time. So I'm not going to do that again. Alright. So if you want to watch that, you can go watch the previous videos, okay? And learn from there. Yes. At evaporation, the next thing that we have to study is nothing but the factors affecting evaporation. Yes, ma'am. I'll just tell the names of it and I'm going to wind up the session. Okay, we'll discuss these factors in the next session. We'll explain these factors in the next session. Just remember, these are the factors that is affecting the evaporation. We can see the evaporation in our daily life, right? We are experiencing evaporation in our daily life. So these are the 4 factors which will be affecting the evaporation. Surface area. Surface area is the first one. Second one is the temperature. Third one is the humidity. Fourth one is the wind speed. Okay. Wind speed. So these are the 4 factors which is affecting the evaporation. So if the surface area increases, evaporation will be more. For example, I have a test tube and a bowl. The evaporation will be more in bowl because the surface area of the bowl is larger than the test tube. I'll explain that in the next session. If I just explain that, your mind will be like, oh God, what are things that she is telling, right? So I'm not going to confuse your minds. I will explain this in next session, okay? So just remember the factors, the 4 factors. There's only 4 factors: surface area, temperature, humidity, and wind speed. And we have animations for that. I'll show you that in the next session. Alright. I hope everything was clear for you, right? Any doubts? Any doubts, anyone? Do you have any doubts?
Yes, Abid.
Abid. Yes, Abid. Are you giving me a bye-bye or was there a doubt?
When we go above the sea level on the top of the mountain, will the altitude decrease from what? Like, will the AU atmospheric pressure decrease from 0?
Yes.
1?
Yes, definitely.
It becomes 0?
See, not become 0, okay? It will not become 0. It will just decrease from point something, 0 point something. Yes. So at sea level, the pressure is 1 atm, and as the mountain, as we go high, the pressure is just going to decrease. And at the sea level, when we go to the bottom of the sea, the pressure will increase. The pressure will be increased in the bottom of the sea. So it will be more than 1 atm. Yes.
Then we can food better below the sea level.
Yes. Can you cook the food under the water? Yes. If you just go under the water, you can cook faster. So you can go underwater and cook faster. All right.
Mehrab,
Definitely,
yes, Mehrab.
that's it. Mehrab, yes, Mehrab.
Ma'am, I had this doubt before, but you didn't let me.
All right, no worries. Just ask me now.
Ma'am, you explained latent heat of fusion, right?
Yes.
Like, so basically, it means like a state where solid converts into liquid without atmospheric pressure, right?
Yes, at the same atmospheric pressure, 1 atm.
And like the melting point will only be 0 degrees Celsius.
Yes, it
go
won't
up or
change.
down.
At the same
And,
pressure and same temperature. It is the latent heat of fusion.
Ma'am, what's the difference between latent, like the normal latent heat and latent heat of fusion?
It is not like that. Latent heat refers to everything, okay? It's a general term, latent heat. And latent heat has subdivisions. Latent heat of fusion, latent heat of vaporization, likewise it will be having subdivisions, okay? There's no difference between latent heat of fusion and latent heat of vaporization, or like latent heat and latent heat of fusion, okay? There's no difference like that. It's just the subdivision of latent heat. Okay.
So basically, latent heat means.
It's one and the same. It's one and the same. It specifically mentioned that 1 kilogram. That is specifically the fusion and evaporation, okay? So latent heat is just the general term. The heat energy required to change the state of matter. That is latent heat. Now specifically talking about latent heat of fusion, the energy required to change 1 kilogram of solid into liquid. That is latent heat of fusion in same atmospheric pressure and temperature.
Thank you, ma'am.
Yes. And John.
Yes, ma'am. So below the sea level, there's a lot of pressure.
High pressure will be there.
Yeah.
Yes, high
More
pressure.
Yeah. So exactly how do they measure with machines how far deep the ocean is than how do they prevent the machines be like squished?
You
Do they have
always,
something which
you always ask these kind of weird questions to me, right? How can I answer this? What kind of mission
okay,
is that?
is it related to the material or is it related to do something in the machine?
Yeah, it's related to the mission. We have so many advanced missions to account all those things, right? We are also advanced. We all have the machineries for that. Yes. All right. Yes, Simon. Sorry. Let me drink some water. Yes.
Nothing, nothing, ma'am. Like I forgot my doubt.
Okay. Hmm? Really? You forgetting your doubt? All right. So, John, you made me to drink water. All right. So, shall we do the exam? Remember this, okay? Remember this. Please do remember
Neha
this.
also, Neha.
Neha.
Ma'am, I think I asked this thing like last to last class.
I don't remember.
See,
I have a memory
have it
problem.
out. It's just I did not note down the physical properties of matter. And that's the slide which I asked you for. You said you would bring it in the last class,
Oh,
but
yes.
I forgot it.
I told you, right? I have memory issues. What was that slide?
The physical properties of matter.
Physical properties of matter. Yes.
Yeah.
Yes. While you do the exam, I'll just get it, okay? Yes. So the exam is activated now. You can just go and attend the exam, okay? Just go and attend the exam. Meanwhile, I'll find a slide for her, okay? Yes, I'm going to find a slide for her. So I'm just going to, yeah. So I'm just going to disappear from the screen to get those slide, okay? Yes, and meanwhile you're going to do the exam, okay? Yes, sir, please do disappear. And the slide, okay? And the slide too. Neha, I got a slide.
Is that the slide in the back? Is
this the one?
Yeah.
Yeah.
Thank you, ma'am. Thank you so much.
How? All right. Yeah, at least thank me. I made such a difficulty to bring the slide up. Yeah. Yes, welcome. Welcome, okay. Alright. Did you take a screenshot of it? Shall I move forward? Yes, the exam. Where is? Why don't you know that? Ma'am got 10 on 10. Very good.
Yes, 6 out of 10, 10 out of 10, 8 out of 10. There are
10 on 10, 10 on 10, 10 on 10. I'm so proud. 6 on 10.
yeah, that's also 6.
6 on 10. You're wrong with the 2 questions, my god.
No, ma'am, because we can't see our mistakes after the exam, but you are discussing.
John is shooting me. John, you did that? Why did you shoot me? Do you want me to act? Ah! Yeah, thank you. We are good at acting, right, John?
You want an Oscar, man?
Yes, definitely. I deserve an Oscar. Right, John? Yes. Thank you. Yes. If you're done with that, give me thumbs up. We'll discuss the questions and I'm going to leave you. It's already 5 minutes late. Someone is really scolding me over there. Why, ma'am? Why can't you follow the timings? Who says that, right, John? John is like, who says that? Yeah. No. Neha is also following that. Okay, I don't. I met you. I want to wear the specs really. I met you. Ma'am, can you read out that comment?
I meant you will shot the child who got 6.
No, I'm not going to scold everyone. I'm not that kind of person scolding everyone. No, I'll not scold. I'm a cool person, right? Yes, so shall we discuss the questions? Shall we discuss it? Is there anyone waiting for me to discuss the question? Then I will answer it and I will score 10 on 10, ma'am, as you wish. Is anyone waiting for that? Never, right? When, ma'am, read that out. Ma'am, can you read that? Where?
Specs, I want to see.
Do you want me to say the wearing spectacles? It will be so fun.
May I give you?
Yeah, I have the spectacles here. Who asked that?
It
Mohammed
was
Zuhair.
Mohammed.
Yeah. How do I look?
No, ma'am. It's not.
It's not matching for my face, right?
Cool personality, even cooler.
It's better you remove it.
Yeah, definitely. It will be better if I remove it.
Yeah,
It's
your
power
hand
glass,
is
I
like-
guess. I'm not able to
Yeah.
see anything. Alright, so we are going to discuss the questions, okay? So here we go, the first question. Which of the following conditions is most favorable for converting gas into liquid? If you get wrong with this, definitely I'm not doing anything. So just answer me. Answer my question. Which is the answer? High pressure and low temperature. Very good. At high pressure and low temperature, we can just convert solid into gas into liquid and liquid into solid. Very good. Which of the following does not affect the rate of evaporation? Your face will be like this. I told you to remember that, right? I've clearly mentioned that. Remember this. I was like, I will ask this question. So, yes, you got the right answer. Insoluble heavy part impurities doesn't affect the rate of evaporation. Temperature increases with? Temperature increases with what? Increases with? Increasing kinetic energy. Don't act more, man. Just tell me the answer and leave us. Yes. And again, head is blasting. The amount of heat energy required to change 1 kilogram of salt into liquid at the pressure or at the atmospheric pressure and at melting point is known as what? Rishikesh? Aha, 3. Yes, a latent heat of fusion. Latent heat of fusion. Very good. Again, the same expressions, right? Same expressions. John, can you make out that expression for me? Perfect. Unit of pressure is what? Very good. Can anyone make out this expression for me? Everyone? Let me check. Everyone make this expression. Do this expression. Yes, definitely. I'm going to bring Oscar in the next class for everyone, okay? Yay. I can see everyone's face. Thank you so much. Yes, very good, children. Very good. Love you all. Very good. And here I have a quote for you. The only way to get what you want in the world is through hard work. So please do work hard in order to achieve something. If you want to achieve something, work hard for it, okay? And work hard on the studies too, because I'm going to ask the questions in the next class. Ta-da! Yes, and we are going to wind up the session. I hope the class was a bit okay for you, right? New students, was the class okay for you? Did you understood everything? Where's the new students? I'm not able to see anymore. Did she left? Really? Yes, there she is. Did you like the class? Yes, I can. It was fun. What about the portions? Did you understood everything? You did. Very good, very good. Yes, let's meet you in the next class. And no hard work, but smart work. Yeah, do any work and study hard. Study smart. Alright. And thank you so much for listening to me. Thank you so much for paying attention in the entire class and well participated during the session. Thank you so much. And I'll meet you in the next session. Until then, take care and bye-bye. Good night.